Hi everyone, and welcome to the final tutorial for Physics 354. Today we're going to be considering the problem of a heavy symmetric top. So in this problem what we consider is a rigid body that's considered heavy. So by this we mean that its point of contact, here the point O, between the rigid body and the surface on which it's rotating remains fixed through time. And since the body is considered to be symmetric, what this means is that two of its moments of inertia are equal. Here we'll say I1 equals I2. We're going to assume that the rigid body is characterized by its principal axes, which will be given, as well as the principal moments. So here the principal axes are denoted by x1, x2, and x3, and the principal moments by I1, I2, and I3. Again, because it's symmetric, we'll set I1 equals to I2, and we're going to assume that these quantities will be given as they characterize this body. Okay, furthermore, we're going to impose some initial conditions on the system, and these will become relevant later. So there's two things that we really want to consider. So the first will be to find the equations of motion governing the dynamics of the system, and the second will be to consider the so-called fast top approximation, and we want to see the sort of impact that those have on the equations of motion for the system. Okay, so now we want to find the equations of motion, and to do so we first want to write down a Lagrangian in terms of some generalized coordinates. We know that for a rigid body in general, there are 6 degrees of freedom, so you need 6 generalized coordinates, right? So generically, right, the rigid body constraint reduces the problem to 6 degrees of freedom from many for generic system of particles in 3 dimensions. So right, the fact that this is considered to be a heavy symmetric top, and moreover the fact that this point of contact is unmoving, actually reduces the problem down to 3 degrees of freedom, such that we only need 3 generalized coordinates to describe the motion of this system. So our Lagrangian will be written in terms of the 3 generalized coordinates. Here we'll use Euler angles, so theta, phi, and psi. And right, so let's just get started. So if we write down the Lagrangian, right, so okay, so first what we want to do, so usually for the rigid body system we have 6 degrees of freedom, so we use this so-called lab frame as well as a body frame, and the body frame is generally, the origin of that is usually set at the center of mass for the system. And in that case, the 6 degrees of freedom will be the sort of components of the position for the center of mass as well as the orientation of that coordinate system with respect to the lab frame. However, here, reiterating sort of what I said before, the constraint that this thing is heavy reduces the degrees of freedom to 3, and it turns out now to be convenient to set the origin of the body frame to actually coincide with the origin of the lab frame. Alternatively, you could choose the origin of the body frame to be at the center of mass still, and then it just kind of ends up looking a little bit different with how the kinetic energy term is sort of partitioned into the so-called translational and rotational. But that's sort of like a small detail. We can discuss more later. Right, so let's write down the Lagrangian for the for the coordinate system that's centered at for the coordinate system that's whose origin is O. And so if we do this, the sort of kinetic term of the Lagrangian will be kind of purely rotational, right? In the sense that the origin of this body frame in this context, right, is not moving. It's the point of contact. So the kinetic term is just some like rotational term, right? Notice that it's not associated with the center of mass here. It's associated with the point O, and then it will be minus some potential energy due to gravity, right? And we know that the potential energy is effectively that acting at the center of mass, right? For this So okay, right. Right, the kinetic the potential term will be like MGL cos theta. So right, recall that L is the distance between O and the center of mass. Okay, so you could just see this term geometrically. This is like the gravitational potential. Sorry, at the center of mass. Okay, now we can express this rotational kinetic energy in terms of the Euler angles. And if we do so, then we see that L will just be a function of L theta phi and psi, right? Because you know this heavy condition, right, and the fact that the potential only depends on the Euler angle theta results in the Lagrangian having this form here. Right, and this is what we would expect from the motivation that I tried to give previous, that this is a system of 3 degrees of freedom, and thus the dynamics should be described by a Lagrangian with 3 generalized coordinates. Okay, so we know how to write down the kinetic energy, rather the rotational kinetic energy, in terms of the Euler angles. So we'll just take that as given. Right, so now this is the Lagrangian we're interested in considering, and notice we've implemented here this symmetric condition, so I1 equals I2. Right, now one important thing to notice is that these moments of inertia are right, yeah, these moments of inertia are in this particular set of these are the moments of inertia in the basis x1, x2, x3 given above. So moments so these are basically like the moments of inertia tensor represented in this like xi basis. And so this is particularly important. So if we just take a moment here to sort of look at this Lagrangian, one thing that we might be interested in doing is thinking about how this Lagrangian compares to that if we chose the body frame to be located at the center of mass. Right. So here we chose the body frame the origin of the body frame to be at this sort of contact point, right? And by definition, that contact point is static, so it appears as though there's only rotational kinetic energy, right? As I sort of wrote down here. One important thing to note, though, is that as I just mentioned below, these moments of inertia I1, I2, I3, or I1 and I3 here, are represented in this basis, right? So this x1, x2, x3 basis, where the origin is at this point of contact. Now, the situation seems to be qualitatively different if we were to set the origin of the body frame at the center of mass, because there you would have what you would call a translational kinetic term associated with the sort of movement of the body frame, right? But it turns out that that would be perfectly compensated by the fact that the rotational term you would write down there would be related to the moments of the inertia tensor represented in that basis. So you would end up writing down the same thing. It would just kind of, the partitioning between rotational kinetic and translational kinetic would just kind of appear different. And maybe this is related to fundamentally at some level. It's really just two different ways of kind of like partitioning one kind of global or one kind of total kinetic energy quantity. Anyways, hopefully that wasn't too confusing, and we'll get back to the problem at hand. So this is the Lagrangian that we were interested in considering, and it's written in terms of the generalized coordinates, theta, psi, and phi, and these are the Euler angles here. Right, so now we want to find the equations of motion. Right, so we have three generalized coordinates. We'll get three equations of motion. The simplest ones are psi and phi, right? Obviously because they're cyclic coordinates. So you'll get conserved quantities associated with each of these degrees of freedom. In a sense, you'll get more precisely, you'll get conserved quantities arising from the minimization of the action with respect to each of these generalized coordinates. So let's look at psi first. So dl by d psi is 0. So dl by d psi dot is equal to theta, right? And this is constant, right? Because the time derivative of this quantity vanishes. So we'll call this I3 times omega 3. So effectively what we're doing is calling this quantity in brackets here omega 3. And this is a conserved quantity as a whole. And we know that I3 is just a constant, so omega 3 is conserved. Great, so that's the Euler angle psi. Now we'll look at phi. So dl by d phi is 0. So if we look at dl by d phi dot, right, this is just implementing the Euler-Lagrange equations. So you should be familiar with this. Right, so you can effectively get these two conserved quantities by implementing this Lagrangian and the Euler-Lagrange equations. So we'll define this constant to be p phi. Okay, right, so now we can go on and find the final equation of motion. And that will be the equation of motion resulting from the Euler-Lagrange equation associated with theta. Right, so it turns out you could just plug away and implement the Euler-Lagrange equation to find the equation of motion for theta. But as is often the case, it's useful to implement one of the symmetries of the system. So in this case, the symmetry that we want to implement is the fact that the Lagrangian has no explicit time dependence, right? So necessarily energy is a conserved quantity. And from that, and using the constants that arose from the Euler-Lagrange equations associated with psi and phi, we should be able to extract the equation of motion for theta in a somewhat more simple way. So since L has no explicit time dependence, we have energy conservation. Right, so if we write down the energy in the usual way, right, in terms of the generalized coordinates and the generalized momenta, we see that well, you could show that it just collapses down to the usual thing, kinetic plus potential energy. So we'll skip that initial step. We'll just write down T rotational plus MGL cos theta. Right, so we'll just sort of plug in what this is. So 1/2 Right, so this is what we have for the total energy, and now what we want to do is implement the constants that we previously found that arose, or the conserved quantities that we found that were associated with the Euler-Lagrange equations for psi and phi. And this will allow us to really just write this as an equation in terms of theta dot and the equation and the constants of motion. Right, so what we do now is we write this term here in terms of the p theta, or p phi and cos theta, and we notice that this here is actually omega 3. And so what we end up getting is the theta dot term remains the same, right? This was not involved. Notice that theta wasn't involved, or theta dot wasn't involved, either here or here. So we keep that term as it is, which makes sense, right? Because we want the equation of motion for theta. And now we have so this should just be all sort of familiar steps from previous things in the course, but we'll just explicitly work through it. Right, and so now what we see is that this whole expression here is just a function of theta and theta dot, and it's useful to rewrite this in the way that we did previous, where we identified an effective potential, right? So this was just 1/2 I1 of theta dot squared plus v effective of theta. So this is just identifying the effective potential in the way that we previously did. And that's just noticing that this whole set of terms here don't depend on any of the generalized velocities and don't depend on psi or phi. Right, so here, just to be explicit, v effective of theta is equal to right. So this is what we have for the effective potential. And we know that this term is just a constant, right? Because omega 3 is a conserved quantity that's what we found previous. So we'll end up just dropping this term. So we could do this, right? We know that the Lagrangian is only unique to a sort of additive constant, so we could just effectively drop constants if we want. So we'll get rid of this term here. Let me just get rid of this guy. And then this, sorry. Right. So now this is the Lagrangian that we're interested in. What is this? Okay. Right. Now, okay, so, right. Now we've implemented these two previous constants, or integrals of motion derived from the Euler-Lagrange equations associated with psi and phi. We still need to find explicitly the equation of motion for theta. And so, right, eventually what we'll end up doing is just taking the time derivative of E and setting that to 0. As we know, it's a conserved quantity, and from that we can extract the sort of theta double dot. But before we do that, it's useful to plug in the initial conditions. So under the initial conditions that we assumed, okay, so generally P phi is cos theta, right? So this is generally what we found above, right up here. But for our initial conditions, we set phi dot equals 0 and theta at 0 is theta naught. Right, so the first of these means that it results in the first term vanishing, right? So the first term equals 0, and then it's plus the second term, right? We know that since p theta is a constant, or p phi is a constant in time, then the second term, this I3 omega 3 cos theta, will be a constant in time. And therefore, if we could evaluate it at any time we choose, and we'll choose to evaluate it at time 0. So this will just be I3 omega 3 cos theta naught, right? Because at time 0, theta is theta naught. And so this is what our value for p phi is, and now we can plug this into the V effective. Right, so in V effective, what we end up having is a term that's like I3 omega 3 cos theta minus p phi, and so this is just I3 omega 3 cos theta minus theta naught. Okay, so now continuing on, we just plug this into V effective, so we end up finding that this is just 1/2 of Okay, so now we have the form for V effective with the initial conditions inserted. And now we can pull this all back together to find the equation of motion for theta. So right, so this means that dE by dt is vanishing. So this is 1/2 I1 d by dt of theta dot squared plus d by dt of V effective of theta, obviously. Now this is like, so d by dt is like d theta dt d by d theta, right? So this is just equal to, right, so this is like d theta by dt d by d theta of theta dot squared. So this is just no, sorry, that's yeah, sorry. So this is just d by dt of sort of like theta. So this is just 2 theta dot theta double dot using the chain rule. Sorry about that. And right, and then we'll use the what I mentioned before on here. So d by dt of kind of V effective of theta is just d theta by dt d by d theta of V effective of theta. Right, so pulling this all together, what we end up finding is that I1 theta double dot is equal to minus d V effective of theta by d theta. Right, just by using that this is equal to theta dot, and then the theta dot terms will cancel. Okay, so this is our equation of motion for the theta degree of freedom, or the theta generalized coordinate rather, and then these were the other two results from the equation of motion for the other two generalized coordinates. Okay, so that's part A of the problem done. Right, and of course, so the form V effective here was just adopted for this form of initial conditions, and that will be implemented in what we do below. So generally, the initial conditions don't really need to be implemented to get the equation of motion for theta dot to be of this form, but it's useful in what we do now. So now we want to work on this so-called fast top approximation. So what we really want to study is how is the equation of motion for the theta generalized coordinate affected by this approximation that I'm writing down now. So, sorry. Right, so this is the so-called fast top approximation, and what we want to do is see how this affects the equations of motion found above. So obviously the equations of motion for psi and phi, I mean the equations of motion just give rise to conserved quantities, right? And of course maybe the explicit form of those conserved quantities might change under this approximation or maybe simplified. But the kind of dynamical expressions are trivial in the sense, right? Like specifically the quantity is just, like the time derivative of the quantity is just 0. So qualitatively, there won't be very much of a change. Quantitatively, of course, things will be different. But really what will be affected by this approximation is the equation of motion for the theta Euler angle. So let's implement this and see what happens to this equation of motion. So, right. Okay. Well, the first thing we might want to know is why is this like so-called like fast top approximation? Well, to be sort of precise, this is only one part of this so-called fast top approximation. And what you could imagine this as. Maybe an easier way to look at this equality, or this inequality rather, is like I3 omega 3 squared over I1 is much greater than MGL. So this sort of right hand side is like the gravitational potential energy, and this left hand side you could imagine as being like associated with the rotational kinetic energy. Right, because right, the rotational kinetic energy is like it's like related to like I omega squared kind of, and this has this side has those same units, right? So you can imagine that this sort of fast top approximation, like one of the consequences of it is that the kinetic terms are much, the kinetic energy is a much greater contribution to the total energy than the gravitational potential energy. So that's really like one way to interpret this approximation. Nonetheless, we're going to implement it and see what happens to this equation of motion for theta. So really what we want to do is study how V effective is affected by this approximation. Right, so if we just write down this V effective in a somewhat different form in order to extract a quantity that's related to this sort of inequality. Okay, so this V effective that we have up here, we can rewrite in this form down here. And so obviously when we do this and we implement this fast top approximation, we have this is approximately 0. So we're going to neglect this second term. Right, so we're going to neglect the second term due to this approximation. And, okay, so All right, so now what we have is okay, so now we have something that looks like this. Now what do we want to do? So first thing to notice is that this term that's remaining is strictly positive for all values of theta, right? So the sort of right, this sort of first factor up front is clearly positive, right? And as is here because everything's squared. So for all values of theta, V effective is positive. And so, right, it has a minimum when theta is equal to theta naught. Right, so this thing is always greater than, it's always greater than or equal to 0, and it equals 0 when theta equals theta naught, mod 2 pi, but let's just say when theta is close to theta naught. So when theta equals theta naught, this is a minimum. Right, so another aspect of this fast top approximation, so further implementing this fast top approximation, what we want to do is say that really the total energy, which is a sum of the kinetic term plus this V effective, right, is really dominated by the kinetic term. Right, and so since this effective term is only a function of the generalized coordinates and no real generalized velocities, we might imagine that the primary contribution to the total energy is from the rotational kinetic energy. So if we go back, if we go back and look here, we might imagine that this contribution, this like kinetic contribution here is much greater than this V effective contribution to the total energy, right? If the top is like quote unquote fast. And as a consequence of that, we want to say that the potential energy is small, and furthermore we want to say that it's near its minimum. So what we'll want to do is do a Taylor series expansion of about theta naught. So alright, so if we go ahead and just do this, so this is, again, so we'll say that this is like fast top. We sort of implement this fast top approximation in sort of two different ways. It's effectively saying the same thing both times we make the approximation, but we'll just make it in sort of two steps here. Alright, so what we have is that this is like I3 squared omega 3 squared over 2 I1. So now we have cos of theta naught plus theta minus. Right, so here eta is going to be an expansion parameter. Right, and so then doing the Taylor series expansions, for cosine and sine, what we end up finding is just I3 squared, omega 3 squared, I1. We'll have, so here we'll have cos theta naught minus eta sine theta naught minus cos theta naught. So we'll explicitly keep only up to linear order in eta. Right, so this here is the Taylor series expansion cos type term, as well with this sort of order eta squared type stuff, which we will neglect. Right. And then this cos and this cos cancel, so what we end up finding is that V effective, which is now a function of this eta, which is just some small angle here, is really like I3 squared over 2I1 eta squared plus order cubed. Right, so we're going to neglect the higher order in eta terms, so that V effective just has this form here. And what we've implemented and going sort of from here to here is we've noticed that this sort of sine term here is squared. So this sine term is squared, so it will cancel with this denominator. Okay, so now we have a form for V effective, and now we just want to plug this into the equation of motion and see what happens to the equation of motion for theta. So the final thing that we want to notice is that eta double dot is equal to theta double dot, because theta naught is constant. Right, so what we end up finding for the equation of motion for theta, let me just write right, so this is minus V effective of eta by d eta. Right, this was by d theta previously, but we set theta to be theta naught, which is constant plus some small parameter, and you can see how the derivative like transforms under this change of variables is just to be d by d eta. So now we plug in V effective here, so this is just minus I3 squared omega 3 squared over I1 eta. Alright, so to leading order in eta, we see that just eta double dot is just minus this I3 omega 3 over I1 squared eta. And you notice that this is like kind of like a simple harmonic oscillator. And so from this we can just identify a nutation frequency. So just like omega is omega 3. Okay, so under this fast top approximation, what we see is that the dynamics of the Euler angle theta is really just like a simple harmonic oscillator. So it's oscillating back and forth with this nutation frequency that we've identified here. So that's really how the sort of fast top approximation boils down. So hopefully, okay, so that's basically it for this tutorial. If you want to find more information about this problem, you could reference the textbook. They tackle the same sort of problem in a little bit of a different way and find somewhat not different results, but they look at qualitatively different things. But just to recap what we looked at here, so we were studying the problem of the heavy symmetric top. Generally, the problem of solving the dynamics of a rigid body is that of 6 degrees of freedom. However, since it's heavy, the consequence of that is that we actually only really have 3 degrees of freedom, right? So the three generalized coordinates we use to describe the system are the Euler angles theta, phi, and psi. We wrote down the Lagrangian associated with this system, and from that we just used the usual Euler-Lagrange equations associated with each of the generalized coordinates to find the equations of motion. We found that since psi and phi are cyclic coordinates, there's conserved quantities associated with each of these. And so really the kind of like interesting dynamics comes in through this theta. And we found the equation of motion for theta. So we just found the equation of motion for theta is kind of governed, or the dynamics of theta is really governed by this effective potential that we were able to identify by implementing the conserved quantities that we previously found for the other generalized coordinates. So in a sense, these things all sort of decouple from one another. And under this fast top approximation, we see that the dynamics of this Euler angle theta is really like a simple harmonic oscillator, and from that we can identify this frequency. Okay, great. So hopefully you guys were all able to stay with me, and if you have any questions, feel free to ask in tutorial, or not in tutorial, sorry, in office hours, or send me an email. Okay, great, thanks.